Tonight, we're going to explore something NASA confirmed that still unsettles the scientists who study it. A single spacecraft, launched before most of us were born, reached a place no instrument had ever touched. And what it found there did not match a single prediction written before it arrived. The universe outside our sun's reach was supposed to be calm, empty, cold, and quiet, fading gently into nothing. But when the numbers came back, nothing about that boundary behaved the way anyone expected. The magnetic field pointed the wrong way. The wall was not shaped like the drawings, and something impossible was waiting on the other side. By the end of tonight, you're going to understand exactly what Voyager 1 detected out there, why NASA took years to admit it, and what that tiny, aging machine is still teaching us about the edge of everything we know. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. So let's begin. The year is 1977. A small machine leaves Earth on a pillar of fire and never looks back. Nobody standing at the launch pad that day could have known what it would become. Not a satellite. Not a probe with a short mission and a quiet retirement. Something closer to a message in a bottle thrown into an ocean with no shore. Its name is Voyager 1. It weighs about the same as a small car. It carries less computing power than a musical greeting card sold today. And it was built, almost by accident, to outlive everyone who built it. For the first 12 years, its job was simple. Fly past Jupiter. Fly past Saturn. Photograph moons nobody had ever seen up close. Send back numbers, and let scientists on the ground turn those numbers into knowledge. It did that job perfectly. It photographed volcanoes erupting on a moon of Jupiter, the first ever seen beyond Earth. It found new rings around Saturn that no telescope had detected. It should have been finished by 1980. Instead, it kept going. Nobody switched it off. Nobody could have, even if they wanted to. Once a spacecraft is moving that fast, in that direction, there is no break, no reverse, no way to call it home. It simply continues, forever, unless something breaks it first. So it kept flying, past the orbit of Saturn, past the reach of Uranus and Neptune, into a region no map had ever properly described. Scientists call this region the outer solar system, but that phrase makes it sound smaller than it is. It is not a place at the edge of a map. It is most of the map. The 8 planets you learned about in school occupy a tiny fraction of the solar system's true size. Beyond them lies a vast, mostly empty region where the sun's influence slowly fades. And somewhere out there, at a distance almost impossible to picture, the sun stops being in charge. That line has a name. The heliopause. It is the true edge of our solar system. Not the last planet, but the last breath of solar wind. For decades, nobody knew exactly where that line was. Nobody knew what it looked like. Nobody knew what waited on the other side of it. Voyager 1 was going to find out, whether anyone had planned for that or not. The sun is not just a source of light. It is also a source of wind. Not wind made of air, but wind made of charged particles, streaming outward from the sun's surface at almost 1,000,000 miles an hour. This solar wind blows outward in every direction at once. It fills the space between the planets. It carves out a bubble around our entire solar system. A bubble that pushes back against the rest of the galaxy. Inside that bubble, the sun is in control. Every planet, every moon, every spacecraft humanity has ever launched has lived its entire existence inside it. Outside the bubble is something else entirely. The space between the stars is not truly empty. It has its own thin gas, left over from stars that died long before our sun was born. It has its own magnetic field, shaped by forces far larger than one star, It has its own pressure, pushing back against the solar wind from the outside. Where the outward push of the sun and the inward push of the galaxy finally cancel out, that is the heliopause. That is the wall. For most of human history, this wall existed only in equations. Scientists could calculate roughly where it should be. They could not confirm it. No instrument had ever been far enough away to check. The estimates varied wildly, by billions of miles, because nobody had ground truth. Voyager 1 was going to become that ground truth, decades after its actual mission had already ended. In December of 2004, 27 years after launch, Voyager 1 crossed the first sign of trouble. The solar wind, which had been blowing past it consistently for its entire journey, suddenly slowed down. Not gradually. Sharply, this was the termination shock, the place where the solar wind first begins to feel the resistance of interstellar space. Scientists had predicted this shock would exist. What they had not predicted was exactly how it would behave when a real spacecraft finally crossed it. The magnetic field jumped. The temperature spiked. The wind that had been racing outward for billions of miles suddenly turned and began moving sideways, deflected by a pressure it could no longer overcome. This was expected, in a general sense, but the exact distance where it happened surprised almost everyone. The termination shock sat nearly 2.5 billion miles farther from the Sun than most models had predicted. That is not a small error. That is an entire extra fraction of the solar system that nobody had accounted for. The bubble around our sun was bigger than anyone had calculated. And bigger, it turned out, was only the beginning of the surprises. Voyager 1 kept moving. Slowly and steadily, it pushed deeper into the strange region beyond the termination shock, a zone scientists call the heliosheath. This region behaves like a thick, turbulent boundary layer, where the solar wind piles up before finally giving way to interstellar space. For 8 more years, the spacecraft crawled through this zone. 8 years, at a speed of over 30,000 miles an hour. That distance alone tells you something about how vast this boundary really is. It is not a line. It is closer to a shoreline stretched across a scale the human mind struggles to hold. And inside that shoreline, the instruments kept recording anomalies that nobody in the original mission planning had ever anticipated. The first anomaly involved shape. Every diagram of the solar system you have ever seen shows a tidy, rounded bubble, like a soap bubble floating gently through space. That image is wrong. Or at least, it is far simpler than reality. When scientists compared the distances at which Voyager 1 and its twin, Voyager 2, eventually crossed the boundary, the numbers did not line up the way a smooth, round bubble would predict. The edge of the solar system is lopsided. It bulges in some directions and compresses in others, shaped by forces pressing unevenly against it from outside. Nobody had built that asymmetry into the early models. Nobody had proof it existed until 2 tiny machines, moving in slightly different directions, sent back numbers that disagreed with a perfect sphere. The second anomaly was even stranger. It involved something scientists nicknamed the magnetic highway. As Voyager 1 approached the true edge of the solar system, instruments detected a region where the magnetic field organized itself into smooth, orderly lines, very different from the chaotic, tangled field found deeper inside the solar wind. Charged particles from inside the solar system were still present in this region. But so were particles from interstellar space, leaking in along those same smooth magnetic lines. It was neither fully inside nor fully outside. It behaved like a corridor, a transition zone, unlike anything predicted in the models built before Voyager reached it. Scientists debated for months whether this magnetic highway meant Voyager had already crossed into interstellar space, or whether it was still trapped in some strange intermediate layer that belonged to neither region cleanly. The debate itself tells you something important. Nobody, Not even the experts who had spent careers preparing for this moment fully understood what a real crossing would look like until it was already happening. The theories had to catch up to the data, not the other way around. Then, on August 25th, 2012, something changed decisively. The density of particles around Voyager 1 jumped, suddenly and sharply, by a factor of 40. Charged particles from the Sun, which had surrounded the spacecraft for its entire life, dropped away almost to nothing. Cosmic rays, high-energy particles from distant, violent events elsewhere in the galaxy, surged upward instead. These cosmic rays are not made by our Sun at all. They come from far more violent sources, exploding stars, distant collisions, and processes so energetic that a single particle can carry more punch than anything ever produced inside our own solar system. Inside the heliosphere, the Sun's own magnetic field acts as a kind of shield, deflecting many of these high-energy particles before they ever reach the inner planets. That is part of why Earth remains relatively protected from the harshest radiation drifting through the wider galaxy. Once Voyager 1 passed beyond that shield, the shielding effect vanished almost immediately, and the instruments recorded a sudden, dramatic rise in exactly the kind of particles the Sun had spent billions of years keeping mostly at bay. This rise did not happen gradually, the way a slow fade might suggest a blurred, uncertain boundary. It happened sharply, within a matter of days, a signature scientists had specifically been watching for. Because a fast transition like that matches the behavior expected at a genuine physical boundary, rather than a slow, ambiguous transition zone. Combined with the equally sudden jump in interstellar density, this cosmic ray surge became one of the strongest pieces of evidence supporting the crossing. Two completely independent measurements. One counting incoming radiation, one measuring density through a borrowed listening instrument, both changing sharply, at almost exactly the same moment, in exactly the way a true boundary crossing would predict. That kind of agreement between separate instruments is rare and valuable in exactly the way scientists hope for but do not always receive. It gave the eventual announcement a foundation sturdy enough to survive the intense scrutiny that a claim this historic was always going to receive. This was the signature scientists had been waiting decades to see. Voyager 1 had left the bubble. It was now traveling through the space between the stars, farther from home than any human-made object had ever traveled. NASA did not announce this immediately. The data needed to be checked and rechecked because a result this large demanded certainty before anyone said it out loud. It took another year before NASA formally confirmed what the instruments were showing. In September of 2013, NASA announced that Voyager 1 had become the first human-made object to enter interstellar space. The headline made it sound simple. A machine had crossed a line. But the anomaly buried inside that announcement was far stranger than the headline suggested. Voyager 1's own instruments for directly measuring plasma density had stopped working decades earlier, back in 1980. The spacecraft could not simply sense the interstellar medium and report a clean number. Instead, scientists had to rely on an indirect method, listening for vibrations in the surrounding plasma triggered by solar eruptions that took months to reach that far. Essentially, they used the spacecraft's radio instrument as an accidental seismograph, listening for a plasma wave rippling through the thin gas around it. When that wave passed by in 2013, its pitch told scientists exactly how dense the surrounding material was. And the density matched interstellar space almost perfectly. This was clever, resourceful science, built from a broken instrument and a spare capability nobody had designed for this purpose. But it also meant the historic confirmation rested on an inference, not a direct reading. That is part of why NASA waited so long before confirming it publicly. They needed the plasma wave event to repeat, to prove the first reading was not a fluke. It repeated. The confirmation held. And that is when the real surprise appeared. The magnetic field, once Voyager crossed into what should have been pure interstellar space, was expected to point in a completely different direction than the field inside the solar bubble. Instead, it barely changed direction at all. The field outside pointed almost exactly the same way as the field inside, a result nobody's models had prepared for. Scientists had assumed the interstellar magnetic field would be independent of the sun's, tilted at a very different angle, because it comes from an entirely different source, shaped by forces across the galaxy rather than by our star. Instead, the two fields lined up, as if something out there had combed the interstellar material into alignment with our own solar system's magnetic structure. This result has never been fully explained. Some scientists believe the sun's magnetic field drapes itself over the outside of the heliopause as it moves through the galaxy, like fabric pulled tight over the outside of a stone. Others believe the boundary itself is not a clean line at all, but a thick, blended region where solar and interstellar fields tangle together for a long stretch before truly separating. Nobody has proven which explanation is correct. The mystery remains open today, still discussed in scientific papers written decades after the initial crossing. An instrument built in the 1970s detected something in 2012 that physicists in 2026 still cannot fully explain. That alone should tell you how strange this frontier really is. We like to imagine the edge of the solar system as a tidy, solved problem. A line on a diagram, confidently drawn. The truth is closer to a coastline mapped by a single boat, sailing through fog, reporting back only what it happens to sail directly through. Everything beyond that narrow path remains a guess, informed by physics, but unconfirmed by direct experience. There is something almost humbling in that. We have telescopes that can photograph galaxies billions of light years away. We have mapped the surface of Mars in more detail than parts of our own ocean floor, and yet the true shape of our own solar system's edge, the boundary of the space we actually live inside, remained genuinely unknown until one aging machine happened to fly through part of it. Let's step back for a moment and consider what it actually took for that machine to still be sending data 47 years after launch. Voyager 1 was built using technology that predates the personal computer. Its onboard computers use a combined memory smaller than what a modern digital photograph would require. Its instructions are updated using software written in an assembly language that most modern engineers have never learned. The engineers who understand its original systems best are now retired, or in some cases, no longer alive. NASA has had to rehire consultants specifically because they remembered how machines like this were built. Manuals from the 1970s printed on paper have been dug out of storage because no digital archive fully replaced them. And still, the spacecraft keeps working. Because it was built by people who assumed failure was not an option they were allowed to plan for. Every component was chosen with redundancy in mind. Every circuit was tested to standards far beyond what a 5-year mission would have required. The engineers building it in the 1970s did not know it would still be flying in 2026. But they built it as if the possibility mattered anyway. Power is the real constraint now. Not distance, and not electronics. Voyager 1 does not run on solar panels, because sunlight this far from the sun is far too weak to power anything. Instead, it carries a radioisotope thermoelectric generator, a device that converts heat from decaying plutonium into electricity. This heat source does not need sunlight, and it does not need moving parts that could wear out or jam. But it does slowly weaken, year after year, as the plutonium inside it gradually decays. Every year, Voyager 1 loses about 4 watts of available power. 4 watts sounds tiny, almost meaningless, barely enough to power a single dim light bulb. But spread across nearly 50 years, that steady loss has forced engineers to make brutal choices. One by one, instruments have been shut down. Not because they broke, but because there was no longer enough power to run them. The camera system was turned off decades ago, after its final images of the outer planets were taken. Heaters keeping certain instruments warm have been shut down deliberately, gambling that components would survive temperatures colder than they were ever designed for. Remarkably, most of them have. NASA engineers now describe their work less as space exploration and more as a slow, careful negotiation with entropy itself. Every choice is about survival, not discovery. Which instrument matters enough to keep alive? Which one can finally go dark, forever, so that others may continue speaking a little longer? It is, in a strange way, one of the most human stories in all of space exploration. Not a triumphant mission of endless expansion, but a slow, dignified decline, managed with as much care as the original launch itself. Now think about distance, because distance is where this story becomes almost impossible to hold in your mind. Voyager 1 is currently more than 14 billion miles from Earth. 14 billion miles. Light itself, the fastest thing in the universe, takes over 22 hours to cross that distance in a single direction. That means a command sent from Earth takes nearly a full day just to arrive. And any response Voyager 1 sends back takes another full day to return. A single round-trip conversation with this spacecraft takes almost 2 days to complete. Imagine asking a single question and waiting nearly 44 hours for the answer to arrive. That is what it means to operate Voyager 1 today. Engineers cannot react quickly to problems. They cannot course correct in real time. Every command must be planned with total certainty, because there is no opportunity to catch a mistake as it happens. If something goes wrong on board, the spacecraft itself must attempt to diagnose and stabilize the problem alone, using instructions written decades earlier, long before anyone could know what specific fault it might one day face. In 2023, Voyager 1 began sending back garbled, meaningless data, a sign that something inside its computer system had failed. Engineers on Earth spent months trying to diagnose the fault from a signal that took over a day just to reach them. They eventually traced the problem to a single corrupted chip inside one of its onboard computers, a piece of hardware that could never be physically inspected, let alone repaired. Their solution was almost unbelievable in its creativity. They rewrote the affected code, splitting it into pieces small enough to be stored elsewhere in the spacecraft's limited remaining memory, and sent the new instructions across 14 billion miles of empty space. It worked. The spacecraft began speaking clearly again, for the first time in months, using a fix designed for hardware built before some of the engineers who wrote it were even born. There is something staggering in that persistence. A machine, alone in the dark for nearly half a century, was essentially given new instructions by people who had to think like the engineers of 1977, using tools and patience that modern space missions rarely require anymore. And it worked, because the spacecraft was built to be understood, adjusted, and trusted, even across an unimaginable gulf of time and distance. Now consider what Voyager 1 is actually carrying with it, out there in that silence. Bolted to its side is a golden record, a physical disc containing sounds and images meant to represent humanity, in case someday someone else out there finds it. The record contains greetings spoken in 55 different languages. It contains the sound of wind, of rain, of a beating human heart. It contains music, chosen carefully by a committee that spent months debating what should represent an entire species to an audience that might never exist. It contains images, etched directly into the metal, showing the shape of a human body, the structure of Dina, the layout of our solar system. It even contains instructions, a kind of scientific diagram explaining how to play the record itself, assuming whoever finds it has ears, or something like ears, capable of understanding sound at all. Carl Sagan, who led the committee that assembled this record, once described it as a bottle thrown into the cosmic ocean. The odds of it ever being found are almost impossibly small. Interstellar space is so vast and so empty that Voyager 1 is not projected to pass near another star system for approximately 40,000 years. 40,000 years, and even then, it will only pass within a light year and a half of that system, not actually enter it. The record was never really built with realistic odds of discovery in mind. It was built as a statement, a message sent more for the sake of sending it than for any expectation of a reply. There is something deeply moving in that choice. A species capable of sending a golden record into a void it knows will likely never be crossed by anyone. Not because it was practical, but because the impulse to reach outward, to say we were here, to leave something behind, apparently matters to us more than the odds of success. Think about the sheer isolation of that spacecraft now, drifting through true darkness. Out where Voyager 1 currently travels, the sun is no longer a warm disk in the sky. It is simply the brightest point of light among countless others, indistinguishable in brightness from many distant stars. There is no day and no night out there, because there is no atmosphere to scatter light, and barely enough light to scatter in the first place. There is no sound, because sound requires a medium to travel through, and the interstellar medium is far too thin to carry anything resembling a wave a human ear could register. If you could somehow stand beside Voyager 1 right now, you would experience something close to absolute silence and near total darkness, broken only by pinpricks of unmoving starlight. The spacecraft itself is small, roughly the size of a compact car, tumbling gently through a void with no reference points, no landmarks, no horizon. It has been traveling in that condition for decades, and it will continue traveling in that condition long after its last instrument finally goes silent. There is no wear from friction out there, because there is essentially nothing to create friction against. There is no erosion, no rust, no weather. Voyager 1 will likely remain largely intact for millions of years, adrift and unpowered, a cold artifact drifting silently through a galaxy that will barely notice it exists. Scientists estimate its power will run out sometime in the early 2030s, when there is no longer enough electricity to operate even a single remaining instrument. At that point, it will stop transmitting. Forever, it will not explode. It will not shut down suddenly, in the way movies often portray machines failing. It will simply grow quieter, transmission by transmission, until one final signal arrives at Earth, and no signal ever follows it again. Engineers already know, more or less, what order the instruments will fail in, because they have modeled the power decline with careful precision. They know approximately which year the plasma wave instrument will lose power. They know approximately which year the last usable heater will fail, exposing critical components to temperatures they were never designed to survive for long. In some sense, humanity already knows the rough shape of Voyager 1's ending, even though the exact final moment cannot be predicted with certainty. It is one of the very few machines in human history whose death has been forecast decades in advance, calculated quietly, almost gently, the way you might describe the coming end of a long winter. And yet, even after its power runs out completely, Voyager 1 will not stop moving. It will continue traveling outward, silently, forever, carrying its golden record with it. Long after every person who built it has died, long after the country that launched it has changed beyond recognition, long after the very language on that golden record might no longer be spoken by anyone on Earth. In a sense, its true mission only really begins after it goes silent. While it transmits, it belongs to us, a tool we use to understand our place in the universe. Once it goes silent, it becomes something else entirely. A message, a time capsule, an object without a country, without a purpose beyond its own continued existence, drifting through a darkness so vast that scale itself starts to lose meaning. Let's widen the frame again, because Voyager 1 is not traveling alone out there. Its twin, Voyager 2, launched just weeks earlier, took a longer, more complicated path, swinging past Uranus and Neptune before eventually crossing into interstellar space of its own, several years after its sibling. Together, the two spacecraft represent something unique in the history of exploration. Two machines, built from nearly identical blueprints, sent in different directions, both still functioning decades later. Both still confirming and contradicting each other's data in ways that keep refining what scientists actually understand about the true edge of our solar system. When Voyager 2 crossed the heliopause in November of 2018, scientists had a second chance to check whether the anomalies found by Voyager 1 were unique, or whether they represented something real and repeatable about the boundary itself. Some readings matched closely, others did not. The termination shock, the magnetic highway, the density jump, all appeared again, in slightly different forms, at a different location, along a different trajectory. This gave scientists their first real proof that the heliopause is not a simple, uniform sphere. It behaves more like a dynamic, breathing structure, expanding and contracting slightly as the sun's activity rises and falls across an 11-year solar cycle. The boundary of our solar system is not fixed. It moves, subtly, in response to forces from both inside and outside our system, a living edge rather than a static wall. Nobody could have known that from a single spacecraft alone. It took two, launched almost as an afterthought of redundancy in the 1970s, to reveal a property of our solar system that remained hidden for the first 4 decades of the space age. There is a lesson buried in that fact, one worth sitting with for a moment. Voyager 2 was never meant to be a backup for Voyager 1. Both were designed as equally important, equally capable machines, sent on genuinely different paths for genuinely different scientific reasons. But because there were two of them, humanity gained something no single spacecraft could have provided alone. A second data point, a second angle, a second chance to be certain about something this important. In science, one measurement is an observation. Two measurements, taken independently, begin to look like a pattern. And a pattern, confirmed across distance and time, begins to look like truth. Now consider the scale of what these two machines have actually witnessed together. Between them, Voyager 1 and Voyager 2 have flown past all 4 of the outer planets, capturing close-up images of worlds that had, until that point, existed only as faint points of light in telescopes. They discovered active volcanoes on a moon of Jupiter, the first confirmed volcanic activity found anywhere beyond Earth. They discovered new, previously unknown moons around Uranus and Neptune. They photographed Neptune's largest moon, Triton, revealing geysers of nitrogen gas erupting from its icy surface, a phenomenon nobody had predicted before the flyby occurred. Voyager 2 remains, to this day, the only spacecraft ever to visit Uranus and Neptune up close. Every textbook image of those two planets, every piece of scientific data used to understand them, originates from a single flyby each, conducted by a machine now considered ancient by modern engineering standards. There are no follow-up missions currently active. There is no updated, higher-resolution imagery on the way anytime soon. Everything we know about the ice giants of our solar system still traces back almost entirely to 2 spacecraft launched in the disco era, using cameras with a fraction of the resolution found in an ordinary modern smartphone. That fact alone says something important about how exploration actually works. It is rarely a smooth, continuous process of constant improvement. It often depends on brief, irreplaceable windows of opportunity, planetary alignments that occur only once every couple of centuries, engineering decisions made decades in advance, and machines built to outlast every reasonable expectation placed upon them. The particular alignment of the outer planets that allowed the Voyager missions to visit all four of them in a single continuous journey will not occur again for approximately 175 years. Whoever eventually attempts a similar mission will be doing so long after everyone alive today has died. In a very real sense, the Voyager missions were not simply well planned. They were a once-in-several-lifetimes opportunity, seized by a small group of scientists and engineers who understood exactly how rare that alignment truly was. Let's widen the frame once more and look at the very first hours of this mission, because the beginning explains so much about why the ending has taken this long to arrive. The summer of 1977 was heavy with heat along the Florida coast. Engineers moved carefully inside a cold, filtered room, assembling a machine that would soon leave every warm room behind forever. Every wire was checked twice. Every bolt was measured to a tolerance far tighter than the mission technically demanded. Nobody in that room was told to expect 50 years of service. They were told to expect 5. But something in the culture of that era, something patient and unhurried, pushed many of them to build well beyond what was strictly required, almost as a form of quiet professional pride. A cheaper part might have satisfied every official requirement on paper. A slightly better part was chosen instead, again and again, not because anyone demanded it, but because the people building this machine understood that once it left the ground, no one would ever touch it again. There would be no second visit, no scheduled maintenance, no replacement part quietly swapped in during a routine inspection. Whatever left the launch pad would be exactly what continued, unchanged, for as long as it managed to survive. That knowledge changes the way a person tightens a bolt, and it changes the way an entire team approaches a project meant to end in 5 years, but secretly built to last much, much longer. On the 20th of August 1977, the first of the 2 spacecraft lifted off the pad, climbing into a clear morning sky, trailing a column of white smoke that leaned gently in the sea wind. 16 days later, on the 5th of September, the second spacecraft followed, carried on a slightly faster trajectory that would eventually let it overtake its twin and reach its planetary targets first. That is why, despite launching second, it carries the name Voyager 1, while the machine that left first became Voyager 2. The numbering follows the order of arrival at their destinations, not the order in which they departed Earth. From the moment those rockets cleared the tower, both spacecraft became something almost entirely defined by numbers. Voltages, temperatures, counts of particles striking a detector. A thin stream of telemetry became the only language available between Earth and these 2 increasingly distant machines. No engineer would ever again see either spacecraft with human eyes. Every judgment about their health, their condition, their continued survival would come entirely from columns of numbers arriving faintly across an ever-growing gulf of empty space. 3 years into the mission, in 1980, the first real sign of mortality appeared. An instrument designed to directly measure the solar wind's plasma stopped responding correctly. Commands were sent to it, exactly as procedure required, and the instrument simply failed to answer. There was no way to repair it. There was no way to even fully diagnose what specifically had gone wrong inside it. The mission simply adapted, rerouting its scientific priorities around the sudden, permanent gap left behind. That failure, small as it seemed at the time, would end up mattering enormously more than 30 years later, when the very same instrument would have been the cleanest possible tool for confirming the crossing into interstellar space. Instead, scientists were forced to improvise, using a different, unrelated instrument in a way nobody had originally designed it for, simply because the tool built specifically for that measurement had already gone silent decades earlier. There is something almost poetic in that gap. A reminder that even the most carefully planned missions are eventually shaped as much by loss and improvisation as by original design. The 5-year mission was completed successfully, exactly as promised, with both spacecraft returning extraordinary images and data from Jupiter and Saturn. Everything that came afterward was, in a very real sense, borrowed time, purchased years in advance by engineers who built for a future they could not fully picture, using judgment rather than certainty. Now let's talk about Jupiter and Saturn themselves, because those early encounters set the tone for everything strange and unexpected that would follow decades later at the edge of the solar system. When Voyager 1 approached Jupiter in 1979, scientists expected a large, mostly uniform ball of gas, colorful but relatively simple in its overall behavior. Instead, the spacecraft's cameras revealed a world in constant, violent motion, storms larger than entire planets churning endlessly across its surface, bands of clouds sliding past each other at wildly different speeds. And then, almost by accident, an image captured the silhouette of one of Jupiter's moons against the blackness of space, revealing something nobody had predicted at all. A plume rising directly off the surface of the moon Io, unmistakably an active volcanic eruption, caught in the act of throwing material high above the ground. It was the first time humanity had ever directly observed volcanic activity happening anywhere beyond planet Earth. Nobody on the mission team had planned specifically to search for this. It was found almost by chance, buried inside a routine navigational image meant for an entirely different purpose. That single accidental discovery reshaped an entire field of planetary science, forcing scientists to reconsider what kinds of geological activity might be common throughout the solar system, rather than unique to our own world. At Saturn, the surprises continued. Voyager 1's closest approach to the planet was deliberately shaped to allow a close pass by Titan, its largest moon, a world wrapped entirely in a thick, orange haze that no telescope had ever managed to see through. That single decision, made years in advance during the earliest mission planning, permanently altered the spacecraft's trajectory, lifting it up and away from the flat plane where the remaining planets orbit. Titan was worth that sacrifice, scientists believed, because a moon with a genuine atmosphere was almost unheard of anywhere else in the solar system. The flyby succeeded, gathering data about Titan's thick nitrogen atmosphere that would shape scientific understanding of that strange, hazy world for decades to come. But the cost was exactly as steep as predicted. Once Saturn's gravity bent Voyager 1's path upward, there was no way to bring it back down again. Uranus and Neptune, worlds its twin would eventually visit, became permanently unreachable for Voyager 1 specifically. It would spend the rest of its journey rising further and further above the plane where the planets travel, climbing toward true interstellar space along a path chosen deliberately, years earlier, for the sake of a single hazy moon. Voyager 2 took the opposite gamble, staying low, remaining close to the plane of the planets, preserving its opportunity to continue on toward Uranus and Neptune, worlds no other spacecraft has visited before or since. Two machines, built from nearly identical blueprints, sent on deliberately different paths, each sacrificing something the other was allowed to keep. There is something almost symbolic in that split. Two siblings launched together, each choosing a different way outward, each finding its own separate set of discoveries, and eventually, each finding its own separate crossing into the dark beyond everything familiar. Let's return now to the specific mystery that gives this story its edge, the anomaly that continues to confuse physicists even now, in 2026. The unexpected alignment of the interstellar magnetic field with our own solar system's magnetic field remains, formally, unresolved. Several competing models attempt to explain it. but none has been confirmed with certainty. One leading idea involves what scientists call magnetic draping, the theory that the sun's own magnetic field wraps itself gently around the outside of the heliopause as our solar system moves through the galaxy, dragging a thin layer of aligned material along with it. Under this model, Voyager 1 has not truly measured the undisturbed interstellar magnetic field at all. It has only measured a distorted layer, shaped by our own sun's passage through the galaxy, and the true unaffected interstellar field may lie somewhere farther out, still unmeasured, still unconfirmed. If that is true, then in a strange sense, Voyager 1 has not yet fully left the sun's influence, even though it has technically crossed the boundary that defines interstellar space. The edge of our solar system, in other words, might not be a single line at all. It might be a blurred, gradual transition, a soft border rather than a sharp one, more like the edge of a shadow than the edge of a wall. Another competing theory suggests the heliopause itself is not stable or smooth, but instead constantly folding and reconnecting, allowing pockets of solar and interstellar material to mix together in complex, shifting patterns. Under this model, Voyager 1 may have passed through a temporary pocket of mixed material, rather than crossing a clean, permanent boundary. If true, the very definition of when Voyager 1 left the solar system becomes far less certain than the confident headlines from 2013 suggested. Neither theory has been proven. Neither theory has been fully disproven either. And here is the part that should genuinely humble us. The only way to resolve this mystery with certainty would require another spacecraft, traveling in yet another direction, confirming or denying these patterns from a third independent vantage point. No such spacecraft currently exists. None is currently funded. None is likely to launch within the working lifetime of anyone reading a description of this mystery today. For the foreseeable future, this remains one of the genuine open questions of modern astrophysics. Sitting quietly, unresolved, at the edge of our own cosmic neighborhood. Not a distant galaxy, not a black hole billions of light years away. The edge of our own solar system, the very boundary of the space we call home. And we still do not fully understand its shape. There is something worth sitting with in that thought before we move further outward. We often imagine scientific knowledge as a straight, steady climb, each generation building smoothly on the last, until eventually everything important becomes known. The truth is messier, and in some ways more beautiful. Sometimes a single aging machine, built with technology that seems almost primitive by today's standards, stumbles into a mystery nobody anticipated. And that mystery simply remains open, patiently waiting for better tools, or better luck, or another spacecraft brave enough, or lucky enough, to fly through the right patch of space at the right time. Let's slow down and look closely at how scientists actually measured density out there. Because the method itself is almost as strange as the discovery it produced. The instrument originally built to measure plasma density directly had failed decades earlier, back in 1980, long before anyone expected it to matter this much. So when Voyager 1 finally crossed into interstellar space, there was no simple dial to read, no clean number waiting to be reported. Scientists had to improvise, using an instrument built for an entirely different purpose, a device meant to listen for radio waves and plasma oscillations, not to measure density directly at all. The trick relies on something plasma does naturally, almost like a struck bell settling into a single, steady pitch. A plasma is a gas that has come apart at the level of its atoms, its electrons and its nuclei, drifting separately, both free to move, both able to be pushed and pulled by passing waves of pressure. When something disturbs that plasma, a solar eruption, for instance, arriving months after it left the sun, the electrons inside it begin to oscillate, swinging back and forth at a very particular frequency. That frequency depends on almost nothing, except how many electrons are packed into a given space. More electrons, a higher pitch. Fewer electrons, a lower pitch. It is a clean, almost musical relationship, one of the first things a plasma physicist learns, and one of the few tools available that could translate a distant vibration into an actual density measurement. The challenge is that space rarely provides a convenient disturbance on command. Scientists had to wait, sometimes for months, for a large solar eruption to leave the Sun, cross the immense distance separating it from Voyager 1, and finally jostle the plasma surrounding the spacecraft enough to produce a measurable oscillation. When that oscillation finally arrived in 2013, the antennas caught it clearly, a faint but unmistakable tone, sitting at a very specific frequency. That frequency translated into a density roughly 40 times higher than what had surrounded the spacecraft just months earlier. Inside the solar wind, a jump that large left little room for doubt. The material around Voyager 1 had changed completely, and the numbers matched almost exactly what scientists expected interstellar space itself to look like. Confirmation did not come from a single event, though. Scientists waited for the pattern to repeat, for another solar eruption to arrive months later and produce another oscillation, another independent confirmation of the same striking result. It repeated. The density held steady at its new, higher level, the signature of a machine no longer sitting inside the thin, outward rushing wind of its home star, but instead sitting inside the far older, far denser material that fills the space between the stars themselves. There is something almost beautiful in how indirect and how patient this confirmation had to be. No dramatic sensor reading, no simple crossing of a visible line, just a faint, borrowed vibration, listened for patiently across months of silence, translated by hand into a number that finally, quietly, confirmed one of the most significant milestones in the history of space exploration. Let's take a moment to compare these distances to something closer to human scale, because the raw numbers alone rarely mean much on their own. If you shrank the entire solar system down until the distance from the Sun to the Earth became just 1 inch, Voyager 1's current distance from the Sun would place it more than a football field away, roughly 100 yards out, still moving steadily outward. If you imagine the Sun as a basketball sitting at one end of a running track, the Earth would be a small grain of sand sitting only about 30 feet away. Voyager 1, on that same scale, would already be well over a mile down the track, still walking, still moving farther with every passing moment. And even at that staggering distance, it remains, technically, still relatively close to home when measured against the scale of the wider galaxy. The nearest star system beyond our own sits more than 4 light-years away, a distance so vast that even traveling at Voyager 1's considerable speed, it would still take tens of thousands of years just to approach it, and even then, only pass nearby rather than actually arrive. Our entire solar system, heliopause and all, sits like a small, quiet room inside a house the size of an entire galaxy, itself only one house among hundreds of billions scattered across a universe whose true size still resists easy description. Voyager 1, for all its historic achievement, has barely stepped outside the front door. And yet, from a human perspective, that single step outside the door remains the single farthest journey any object built by human hands has ever completed. There is no contradiction in holding both of those truths at once. A journey can be almost unimaginably vast by human standards, and still be almost nothing at all by the standards of the universe it moves through. Both facts are true, simultaneously, and both are worth sitting with quietly for a moment before moving on. There is one more comparison worth adding, quietly, before we continue. Light from our own sun takes roughly 8 minutes to reach Earth. A delay so small most people never think about it at all. Light from Voyager 1 takes over 22 hours to reach Earth. A delay so large, it reshapes the entire rhythm of how the mission must be managed. Between those two numbers sits almost the entire practical difference between living inside a solar system and beginning to leave one. 8 minutes feels almost instant. 22 hours feels like an entirely different relationship with time itself. One where patience is not a virtue so much as a basic requirement for participating at all. Voyager 1 lives permanently on the far side of that difference now, and has for decades quietly redefining what patience even means for the small team still listening for it back home. Now let's widen the scale even further, beyond the mystery itself, and consider what it means that a machine built in the 1970s is still the primary source of direct, in-place measurements from beyond our solar system. Every other instrument studying interstellar space does so remotely, using telescopes, using theoretical models, using indirect observations of starlight passing through distant gas clouds. Voyager 1 and Voyager 2 remain the only instruments ever built that have physically been there. Sensors immersed directly in the material itself, rather than observing it from a comfortable distance. There is a profound difference between studying something from far away and actually standing inside it. Even if standing is not quite the right word for a machine tumbling silently through the dark. Every measurement Voyager 1 sends back carries a kind of authority that no telescope, however powerful, can fully replicate. It is not a calculation. It is not an estimate. It is a direct report from inside the very thing being studied. And because of that, even a single garbled data point from Voyager 1 carries enormous scientific weight. Weight that engineers fight to protect, year after year, decision after careful decision, as the spacecraft's power continues its slow, irreversible decline. Let's slow down for a moment and look more closely at the physics powering this entire, impossible endurance. Voyager 1 does not carry batteries in the way you might imagine batteries. A battery, you know, stores energy that was placed into it. Energy that runs out once it is used. Voyager 1 instead carries a small quantity of plutonium, a heavy, unstable element that naturally breaks apart over time, releasing heat as it does. This process is called radioactive decay, and it happens whether anyone asks it to or not. The plutonium does not need sunlight. It does not need fuel added to it. It does not need anything from the outside at all. It simply decays, steadily, predictably, releasing warmth the way a dying ember releases warmth long after the flame itself has gone out. Engineers surround that warmth with a device called a thermoelectric generator, a set of materials that convert a temperature difference directly into electricity, with no moving parts, no pistons, no gears to wear down or seize. This is part of why the system has lasted so long. There is almost nothing inside it that can mechanically break. No bearing to wear thin, no fluid to leak away. Only atoms, quietly falling apart, at a rate written into the laws of physics themselves, unconcerned with mission schedules or human expectations. But that same steady process is also, unavoidably, a countdown. Plutonium decays on a fixed timetable. A timetable known before the spacecraft ever left Earth. Every year, without exception, the heat produced grows slightly weaker. Every year, the electricity available to Voyager 1 grows slightly smaller. There is no way to slow this decline, and there is no way to reverse it. It cannot be repaired, refueled, or replaced, not by any mission, not by any future spacecraft, not by any act of human ingenuity, because nothing can travel to Voyager 1 and physically service it. It is, quite literally, running on borrowed time that was fully accounted for before the countdown even began. Engineers in the 1970s knew this. They built the mission around a 5-year requirement, using an amount of plutonium they expected to comfortably outlast that requirement. What they could not have known, not with certainty, was just how conservatively they had estimated everything else. every part chosen for redundancy, every component selected slightly stronger than the mission strictly required. That quiet over-engineering is the real reason Voyager 1 is still speaking to us today, decades past its formal expiration. Not luck. Discipline. Now think about what that slow decline actually costs the mission. Instrument by instrument, choice by choice. In the early years, Voyager 1 ran cameras, spectrometers, plasma detectors, magnetometers, and multiple other instruments simultaneously, all drawing power at once. As the decades passed, engineers were forced into a kind of triage, deciding which instruments mattered enough to keep alive, and which had to be sacrificed so others could continue. The cameras were the first major loss, switched off deliberately after the final images of the outer planets were captured, because there was simply nothing left to photograph that justified the power they required. Some instruments failed on their own, quietly, without warning, the way the plasma detector failed in 1980, leaving a permanent gap in what the spacecraft could measure directly. Other instruments were shut down on purpose, in careful, calculated stages, as engineers worked to stretch the remaining power across as many active years as possible. Heaters, too, were eventually switched off, exposing delicate components to temperatures colder than anything they were originally designed to survive. Astonishingly, many of them kept working anyway, colder than intended, dimmer than intended, but still transmitting. This is not how most machines behave when pushed beyond their design limits. Most machines fail loudly and immediately. Voyager 1 instead seems to fail gracefully, one small piece at a time, adapting quietly to conditions nobody originally planned for. Some engineers who have worked on the mission for decades describe this behavior with something close to affection, almost as if the spacecraft itself has developed a kind of stubborn, patient resilience that goes beyond its original design specifications. Of course, it has not developed anything. It has no awareness, no will, no desire to continue. But the humans watching it, generation after generation of them, cannot help but read a kind of quiet endurance into its behavior, because that endurance is, in its own way, deeply human in origin, even if the machine itself feels nothing at all. Let's look now at distance again, because distance is the one thing about this mission that never stops growing. Voyager 1 moves away from Earth at roughly 38,000 miles an hour, a speed almost impossible to picture using anything familiar. At that speed, it would circle the entire Earth in under an hour. At that speed, it would cross the distance between New York and Los Angeles in under 5 minutes. And yet, even moving that fast, every single day, it becomes just a little bit harder to reach. Every day, the distance between Voyager 1 and Earth grows by roughly 1 million miles. 1 million miles added to an already unimaginable total, every single day, without pause, without exception, for nearly 50 years running. There is no day off. There is no slowing down to rest. The spacecraft simply continues, carried entirely by momentum it was given decades ago, a momentum that will likely outlast every structure currently standing on Earth. Because there is essentially nothing out there to slow it down. No friction, no atmosphere, no resistance of any meaningful kind. Voyager 1 will likely continue moving at roughly this same speed for millions of years into the future, long after its instruments have gone silent, long after its power has fully run out. Try to hold that thought for a moment. A machine, built by human hands, using tools from an era before personal computers existed, will likely still be moving through space, roughly along its current path, for a length of time that dwarfs all of recorded human history, combined many times over. Every empire that has ever risen and fallen on Earth. Every language that has ever been spoken and forgotten. Every civilization that has ever built something meant to last will, statistically, be gone and forgotten long before Voyager 1 physically deteriorates enough to stop existing as a coherent object. It is not exaggeration to call it one of the most durable objects humanity has ever created. It may, quite plausibly, outlast the species that built it. Now let's think again about that radio silence. That strange, patient conversation stretched across nearly 2 full days for a single exchange. Imagine, for a moment, an engineer on Earth noticing something unusual in a stream of numbers arriving from Voyager 1. A voltage slightly outside its expected range. A temperature reading drifting somewhere it should not be drifting. That engineer cannot simply issue an instruction and watch the spacecraft respond immediately. They must first confirm the anomaly is real, checking it against historical patterns, ruling out simple noise in the signal itself. Then they must carefully draft a command, review it, and review it again, because a mistake sent across 14 billion miles cannot be quickly corrected. Then that command begins its journey outward, traveling at the speed of light, the fastest anything in the universe is capable of moving, and it still takes over 22 hours to arrive. The spacecraft receives it, processes it, and responds, and that response begins its own 22-hour journey home. An entire day, sometimes closer to 2 full days, passes between a single question and a single answer. There is no version of urgency that survives contact with a distance like that. Every decision made about Voyager 1 today is made slowly, deliberately, with a kind of patience that feels almost foreign in a world built increasingly around instant response. In some ways, working with Voyager 1 forces its engineers into a completely different relationship with time itself, one closer to the patience of an astronomer or perhaps a geologist than the patience of anyone working with modern, real-time technology. You cannot rush a conversation with something 14 billion miles away. You can only prepare carefully, send your message, and wait. Let's return now to the golden record, because there is more to it than a simple list of sounds and images, and its full story deserves more room than a passing mention. The record itself is made of gold-plated copper, chosen specifically because it resists corrosion far longer than almost any other practical material available at the time. Etched onto its surface are instructions, symbols meant to explain, without relying on any spoken language, exactly how the record should be played. The idea assumes an intelligence capable of reasoning through basic physics and mathematics, symbols meant to be universal even if language itself is not. Whether that assumption is realistic is of course entirely unknown, and always will be. Inside the record are 90 minutes of music, chosen from cultures all across the globe, spanning centuries, spanning continents, spanning instruments built from wood, from metal, from human voices alone. There are recordings of a mother's first words to her newborn child. There is laughter, unscripted, recorded simply because laughter itself felt like something worth preserving, something that said as much about being human as any formal statement ever could. There are sounds from nature, thunder rolling across an open plain, waves breaking against a shoreline, the calls of animals that exist nowhere else in the known universe. There is a recording of a human brainwave pattern, translated into sound, an attempt, almost poetic in its ambition, to let a future listener experience something close to a fragment of human thought itself. The scientists who assembled it knew, with near certainty, that the odds of it ever being found were vanishingly small. Interstellar space is so vast that even a message traveling for tens of thousands of years is unlikely to pass near enough to anything capable of noticing it. They built it anyway. Not because they expected success in any conventional sense, but because the act of trying, the act of reaching outward with genuine care and genuine hope, seemed to matter on its own terms, independent of whether anyone would ever actually hear it. There is a kind of quiet philosophy embedded in that decision, one worth sitting with for a moment before we continue. We are a species capable of imagining an audience that may never exist. and choosing, deliberately, to prepare a message for it anyway. Not because logic demanded it, because something deeper than logic seemed to ask for it. Let's talk for a moment about the people behind this mission. Because a machine this old requires a very particular kind of human patience to keep alive. Many of the engineers who originally designed Voyager 1 systems have long since retired. Some have passed away. The team currently operating the spacecraft is, in many cases, decades younger than the mission itself, inheriting systems built before they were born, using documentation that sometimes exists only on fragile, decades-old paper. There is something almost archaeological about their work. They are not simply operating a spacecraft. They are interpreting the intentions of engineers who are no longer available to explain their own choices, using logic, deduction, and a deep respect for a design philosophy from an entirely different era of engineering. When something breaks, there is no manufacturer to call, no updated replacement part to order. There is only the original schematic, the original code, and the accumulated wisdom of a team that has learned to think the way its long-departed predecessors once thought. In a very real sense, keeping Voyager 1 alive today is an act of translation, carrying forward not just data, but a mindset, a discipline, a way of building things meant to last far longer than anyone reasonably expects. NASA has openly stated that operating Voyager today requires specialized skills that are becoming increasingly rare. Younger engineers are sometimes brought in specifically to learn these older systems before the last remaining experts retire completely, ensuring some form of institutional memory survives even after direct experience does not. There is a quiet urgency to this work that rarely makes headlines. Every year, the team operating Voyager 1 faces a genuine possibility that this could be the year the spacecraft finally falls silent. Every year it does not. Feels less like an expectation and more like an unexpected gift, carefully protected by people who understand exactly how fragile that continuity truly is. Let's return to the number that anchors this entire story. The number that makes everything about Voyager 1 feel almost unbelievable. 47 years. 47 years of continuous operation, through failing components, through fading power, through distances that grow larger with every single day that passes. Few human-made objects of any kind survive that long in active use, let alone objects operating in one of the most hostile, unforgiving environments imaginable. There are buildings on Earth that have not survived 47 years without major renovation. There are entire technologies that have become completely obsolete and forgotten within that same span of time. And yet out there, alone, in absolute cold and absolute silence, a machine built using slide rules and hand-soldered circuits continues, faithfully, to do exactly what it was told to do, decade after decade, without complaint, without deviation, without anything resembling doubt. There is no ego in that persistence, no frustration, no fatigue, no growing weariness with the endless dark. Voyager 1 does not know it is remarkable. It does not know it carries a message meant for beings it will almost certainly never meet. It does not know it has already outlived the mission planner's wildest original expectations by nearly a full decade for every year its original mission was ever supposed to last. It simply continues, executing instructions written by people who are mostly gone now, carrying a golden record meant for an audience that may never exist, drifting through a boundary that scientists still do not fully understand, at a distance that light itself takes nearly a full day to cross. And someday, likely sometime in the early 2030s, that continuation will finally stop. Not with drama. Not with a final dramatic transmission worthy of a film. Simply, quietly, as the last available watt of power finally runs out, and the last faint signal fades into the same silence that surrounds it. After that, Voyager 1 will not stop existing. It will simply stop speaking. It will continue moving outward, forever, carrying its golden record, its faded instruments, its silent testimony to a species that once looked upward and outward and decided the unknown was worth reaching toward, even without any guarantee of ever understanding what it found there. Let's widen the frame once more, past the edge of our own solar system, out to the scale of the galaxy that contains it. Our Sun is only one star among roughly 200 billion stars inside the Milky Way. A spiral disk of light so large that light itself takes about 100,000 years to cross it from edge to edge. Voyager 1, moving faster than almost any object ever built by human hands, would still need tens of thousands of years just to reach the nearest neighboring star, and that star is barely a doorstep compared to the true size of our galactic home. Our entire solar system, heliopause included, orbits the center of that galaxy once every 225 million years or so. A single lap so slow that the last time we completed one, dinosaurs had not yet appeared on Earth. Everything Voyager 1 has ever measured, every anomaly it has detected, every mystery it has raised, has occurred within a distance so small, relative to the galaxy itself, that it barely registers as a fraction of a percent of the journey between stars. And the galaxy itself is only one among hundreds of billions of galaxies, scattered across a universe whose true edges, if it even has edges in any meaningful sense, remain unknown to anyone. Light from the most distant galaxies ever observed has been traveling toward us for more than 13 billion years. Meaning, we see those galaxies not as they are now, but as they existed almost at the very beginning of the universe itself. Compared to a number like that, 14 billion miles feels almost intimate, almost close, a distance you could nearly hold in your mind without it slipping away entirely. And yet it took a machine built from 1970s technology nearly half a century of continuous flight just to cover that single, comparatively small step. There is a kind of vertigo in holding both scales at once, the achievement and the smallness of it, the record-breaking distance, and the fact that it remains, cosmically speaking, barely a step past the front door. Try picturing it one more way, gently, without rushing. Imagine every mile Voyager 1 has traveled represented by a single grain of sand. 14 billion grains would fill more than enough buckets to cover a small beach, buckets stacked patiently, one after another, each one representing years of silent, uneventful travel through the dark. And even that entire beach, however large it might feel standing in front of it, would still sit inside a much larger shoreline, representing the distance to even the nearest star. A shoreline so long that our imagined beach would appear only as a single small patch near one end of it. Distances like this are not really meant to be pictured all at once. They are meant to be approached slowly, patiently, one comparison at a time. The same patient way the spacecraft itself has covered them, one quiet mile after another, for nearly 50 uninterrupted years. Most people will never consciously think about the heliopause. Most people will go through entire lives without ever learning that the edge of our solar system was mapped, imperfectly, by two aging machines drifting slowly outward through the dark. And yet, every single one of us lives inside that bubble, every day, without noticing it, protected from the wider galaxy by a wall of solar wind we cannot see, cannot feel, and rarely think about at all. Voyager 1 gave that invisible wall a shape, however uncertain, however still debated. It gave scientists real numbers to argue over, instead of only theories built from assumption. It turned an abstract boundary into something measured, however imperfectly, by an actual machine that had actually been there. That is not a small thing, even if it rarely makes headlines outside the world of astrophysics. Let's think, for a moment, about what this mission says about the particular kind of patience required to study the universe honestly. Modern life moves quickly. Information arrives instantly. Decisions are expected immediately. And most technology is built to be replaced within a handful of years, not maintained carefully across half a century. Voyager 1 stands as a quiet counterexample to almost everything that pattern represents. It was built slowly, tested exhaustively, and launched with no expectation of quick results. Its most important discoveries did not arrive within months, or even years, but across entire decades, accumulated slowly, checked repeatedly, confirmed only when the evidence became truly undeniable. The scientists who first designed its instruments in the 1970s could not have personally witnessed its crossing into interstellar space in 2012, not because of any failure, but simply because so much time separated the two events that entire careers rose and ended in between. Some of the people who worked on the original mission passed away long before Voyager 1 ever reached the boundary they had spent years preparing it to study. Others lived just long enough to see it happen, decades after their own direct involvement had ended. Watching from retirement as headlines finally confirmed what they had helped make possible so long ago. There is something quietly moving in that timeline. A reminder that some forms of discovery cannot be rushed, no matter how much we might wish otherwise. Some questions can only be answered by people willing to build something today that will not deliver its full answer until long after they themselves are gone. That kind of patience is rare. It goes against nearly every instinct modern life tends to reward. And yet it produced one of the most significant scientific achievements in the history of space exploration. A boundary measured, a mystery uncovered, a message sent outward, carried by a machine nobody alive today will ever personally see reach its next meaningful milestone. Let's think, too, about what it means that this entire achievement rests on machines that were never meant to still be working. There is no version of the original Voyager mission plan that included the phrase interstellar space. That phrase came later, added by circumstance, by unexpected survival, by a spacecraft that simply refused to stop functioning when its formal assignment ended. Nobody designed Voyager 1 specifically to measure the heliopause. They designed it to photograph planets, and the heliopause crossing became possible only because the spacecraft happened to still be alive, decades later, exactly when it happened to arrive at exactly the right place. That is worth remembering, because it reframes the entire achievement. This was not a mission built around a single, planned discovery. It was a mission built around careful, deliberate engineering. Engineering good enough that it eventually stumbled into a discovery nobody had specifically planned for. Sometimes the most important discoveries are not the ones we set out looking for. Sometimes they are simply the reward for building something well enough, and patiently enough, that it survives long enough to find them almost by accident. Let's go back one more time to the instruments themselves, because there is one more anomaly worth sitting with before we finish this journey. When Voyager 2 finally crossed into interstellar space in 2018, its still functioning plasma instrument allowed scientists to measure something Voyager 1 never could: the actual temperature of the material surrounding it. The number that came back was strange enough to make experienced physicists pause. Roughly 30,000 Kelvin, sometimes measured even higher, a temperature far hotter than the surface of our own sun. And yet the spacecraft itself remained cold, its instruments unharmed, its systems entirely unaffected by heat of any kind. This sounds like a contradiction, until you remember that temperature and heat are not quite the same thing. Temperature measures how fast individual particles move. Heat measures how much energy is actually transferred when those particles collide with something. Out where Voyager 2 travels, the interstellar medium is so thin, so close to a true vacuum, that individual particles rarely collide with anything at all. Each particle moves with tremendous, genuine violence. But there are so few particles in any given space that violence never accumulates into anything resembling real, transferable heat. It is a little like standing in a nearly empty room where a handful of very fast bullets occasionally cross the space, rather than standing inside a furnace packed with matter. The individual speed is extreme. The overall danger, in terms of heat transfer, is almost nothing. Scientists sometimes nickname this region the fire hose wall, a name that captures both the astonishing measured temperature and the surprising harmlessness of it at the same time. It is, in its own way, one of the strangest environments ever directly measured by any human instrument. A place simultaneously hotter than a star and gentler than open air. There is a second surprise buried inside that same data. Many scientists expected the boundary crossing to produce turbulence, a churning, chaotic mixing of solar and interstellar material as the two very different environments collided. Some turbulence was found, but far less than many models predicted, and in some directions, almost none at all. The transition, in places, looked closer to a calm, steady handoff than a violent collision. That calm was almost as surprising as violence would have been, because nearly every other boundary layer studied in physics, whether in a laboratory, in Earth's own atmosphere, or in distant astrophysical systems, tends to produce at least some degree of visible turbulence at the meeting point of two different flows. Finding a boundary that behaves more calmly than expected raised just as many new questions as a boundary that behaved more violently would have. Nobody has fully explained why some sections of this crossing appear so orderly, while other measurements, like the aligned magnetic field, suggest a boundary far stranger and more complex than any simple model can currently capture. Every answer Voyager provides seems to open at least one new question behind it, a pattern that has repeated at nearly every stage of this decades-long journey. Let's slow down one final time and think about what all of this actually means for the two machines themselves, quietly continuing their work, indifferent to the debates unfolding about them back on Earth. Neither spacecraft has any awareness of the mysteries it has created. Neither one experiences anything resembling curiosity, or pride, or wonder at what it has found. They are simply following instructions written decades ago, executing the same basic loop of tasks over and over, for as long as their remaining power allows it. And yet, somehow that simplicity makes their story even more remarkable, rather than less. Everything meaningful about this journey, every ounce of wonder, every unanswered question, every quiet philosophical weight carried by a golden record aimed at no one in particular, exists entirely because of the humans who built these machines. And the humans still watching from home, decades later, still listening for whatever faint signal comes next. The spacecraft themselves are indifferent. We are not. And that difference, that gap between a machine simply continuing and a species that cannot stop searching for meaning in that continuation, might be the truest discovery this entire mission has ever produced. Let's return briefly to Earth and to the specific room where all of this is still being watched, day after day, decade after decade. The Deep Space Network is the system NASA relies on to speak with Voyager 1 at all, a collection of enormous dish antennas positioned carefully around the globe. In California, in Spain, and in Australia. They are spaced roughly 1/3 of the way around the planet from each other, deliberately, so that as Earth rotates, at least one of them always has a clear line of sight toward the tiny, distant spacecraft. Without that careful spacing, Earth's own rotation would regularly block the signal, cutting off contact for hours at a time as the correct patch of sky rotated out of view. These dishes are enormous, some stretching over 200 feet across, built specifically to catch a signal so faint that describing its strength in ordinary terms barely makes sense. By the time Voyager 1's transmission reaches Earth, its signal has weakened to a fraction of a billionth of a watt. Engineers sometimes compare it to trying to detect the power of a refrigerator light bulb, if that bulb were located on the surface of Pluto, rather than inside your kitchen. That comparison is almost absurd on its face, and yet it is the literal scale of engineering required simply to hear this spacecraft speak. Every single word of data received from Voyager 1 today represents an extraordinary act of listening, performed by dishes originally built decades ago, upgraded repeatedly over the years, straining to catch a whisper, crossing an almost incomprehensible gulf of empty space. There is a quiet, unglamorous heroism in that work, one that rarely appears in dramatic retellings of space exploration. No astronauts, no dramatic countdowns, only patient engineers and enormous dishes pointed carefully at a single point in the sky, listening for a signal that grows fainter every single year, straining just a little harder each time to hear a spacecraft that is, quite literally, running out of things left to say. Let's consider, too, what happens on the rare occasions when that signal briefly disappears altogether. Because it has happened more than once in recent years, and each time, it forces the entire team to confront the mission's mortality directly. In 2023, when Voyager 1 began transmitting nothing but meaningless, garbled data, engineers spent months working through the problem with a patience that modern technology rarely demands anymore. Every diagnostic step required sending a command and waiting nearly 2 full days for any kind of response. Some tests failed to produce useful information at all, forcing the team to design an entirely new diagnostic approach, then wait another 2 days simply to learn whether that new approach had worked. It was, by any modern standard, an almost unbearably slow process, closer to solving a puzzle through the mail than debugging a piece of modern software. And yet eventually, the team traced the fault to a single failed chip, buried inside one of the spacecraft's aging onboard computers, a piece of memory that could store only a small fraction of what a single failed chip might store in almost any modern device. Because that chip could not be repaired, the only option left was almost unthinkable by modern engineering standards. Rewrite the affected code entirely, splitting it carefully across whatever undamaged memory remained scattered elsewhere in the spacecraft's extremely limited storage. Every choice in that rewritten code had to account for constraints that most engineers today have never had to consider, working within kilobytes rather than gigabytes, treating every single bit of available memory as something precious and finite. When the new code was finally sent outward, engineers could do nothing but wait, again, for nearly 2 full days, not knowing whether their solution would work or whether this particular failure might finally mark the beginning of the end. It worked. Clear, coherent data began arriving again, proof that a team of modern engineers could still think patiently and carefully in the exact language of hardware built nearly 50 years earlier. There is something almost moving in that success. A reminder that expertise does not always mean using the newest tools available. Sometimes it means understanding an old tool so completely that you can still repair it decades after everyone assumed nobody would ever need to again. Let's think, finally, about what it means to be the team responsible for deciding, one instrument at a time, what Voyager 1 gets to keep and what it must eventually lose. Every year, as available power continues its slow, predictable decline, engineers face the same difficult question all over again. Which instrument matters enough to protect, even at the cost of another? These are not easy decisions, and they are rarely made quickly. Teams debate the relative scientific value of each remaining instrument, weighing what unique data it still provides against how much power it currently requires to keep functioning. Sometimes an instrument is kept alive slightly longer than planned, because a particular measurement suddenly becomes scientifically important in a way nobody anticipated when the original power budget was first drafted. Other times, a difficult decision is made to switch something off entirely, even while it is still functioning perfectly well, simply because the power it uses is needed elsewhere to protect a different, more critical system for a few more precious years. There is no version of this process that feels comfortable. Every choice involves accepting a real, permanent loss in exchange for a small amount of additional time for something else. And every single year, the list of remaining choices grows shorter, the margins grow thinner, and the conversations grow a little more serious. Engineers openly acknowledge that within the next several years, the spacecraft will likely no longer have enough power to operate even a single scientific instrument. At that point, all that remains will be a faint, simple radio signal, confirming only that the spacecraft still exists, still functions at the most basic level, still drifts onward through the dark. Even that simple signal, engineers know, will not last forever. Eventually, even the smallest remaining systems will lose the tiny amount of power required to keep transmitting at all. And when that day finally arrives, there will be no dramatic final message, no farewell broadcast crafted for the occasion. There will simply be one final, ordinary transmission, followed by silence. The same silence that has surrounded this spacecraft for nearly 50 years, closing in completely for the first time. Let's return, once more, to Titan, because that single, hazy moon shaped the entire remainder of Voyager 1's journey, and its story deserves a closer look. Before Voyager arrived, almost nothing was known about Titan's surface, because the thick orange haze surrounding it blocked every telescope ever pointed toward it. Some scientists speculated it might hold oceans, not of water, but of liquid methane and ethane, chemicals that remain liquid only in conditions far colder than anything found on Earth. Others believed the haze itself might hide a surface covered entirely in organic material, a kind of frozen chemical laboratory, sitting quietly at the outer edge of the solar system. Nobody knew for certain, and that uncertainty made Titan one of the most tantalizing targets in the entire outer solar system. The trajectory required to study it properly demanded that Voyager 1 pass directly behind the Moon as seen from Earth, threading a needle in space with almost no room for error. For those few critical minutes, radio signals sent from the spacecraft back toward Earth would have to pass directly through Titan's thick atmosphere, bending and slowing in ways that revealed its density, its temperature, and its structure, layer by layer. The maneuver worked exactly as planned. Titan's atmosphere turned out to be far thicker than Earth's own, composed mostly of nitrogen, wrapped in a haze so complete that Voyager 1's cameras could not see through it to the surface below at all. That single flyby generated scientific interest that lasted for decades, eventually inspiring an entirely separate mission, one that would not arrive at Saturn until more than 20 years later, carrying a small lander built specifically to finally touch Titan's hidden surface. None of that would have happened without Voyager 1's original sacrificial choice. A decision made years in advance, trading 4 entire planets for one uncertain, hazy moon. It is worth remembering that trade every time we discuss the anomalies Voyager 1 later discovered at the true edge of the solar system. Because that entire later chapter of the mission only became possible due to the specific, upward trajectory Titan required. Had Titan never been prioritized, Voyager 1 might have remained closer to the plane of the planets, following a path that could have led it toward an entirely different, and perhaps far less mysterious, crossing into interstellar space. Sometimes the strangest discoveries in science are not the direct result of careful planning toward a specific goal. Sometimes they are the indirect result of an entirely different decision, made for entirely different reasons, years before anyone could have known where it would eventually lead. Let's think too about scale one more time, but from a slightly different angle. The angle of raw human effort rather than raw distance. Thousands of people have worked on the Voyager mission across its nearly 50-year history, from the original engineers who built it, to the current, much smaller team still carefully guiding its final years. Each of them contributed a small piece to something none of them could ever fully experience alone. Nobody who worked on the original 1977 launch could have personally witnessed every discovery that followed, spread as they are across 5 decades of continuous operation. Nobody currently working on the mission today was present for its beginning. The full story of Voyager 1 exists nowhere inside a single human mind. It exists only across an unbroken chain of people, each one picking up where the last one left off, each one adding a small piece to a story too large for any single lifetime to fully contain. That too feels like a kind of message, quieter than the golden record, but no less meaningful. Some things worth doing cannot be completed within a single human lifetime. They require handing the work forward, carefully, patiently, trusting people you will never personally know to continue something you began, but will not live to see finished. Voyager 1 itself is an object built almost entirely out of that kind of trust. Trust between generations of engineers. Trust across nearly 50 years of continuous, careful stewardship. Trust that the work still mattered, even decades after the original 5-year mission had been completed and forgotten by almost everyone outside the small community still paying close attention. Let's think one final time about the golden record, because there is a particular detail about it that captures something essential about this entire mission. Among the images etched into its surface is a simple diagram showing the position of our sun relative to a set of nearby pulsars, stars that spin rapidly and emit extremely precise, regular bursts of radiation. Because pulsars spin at very specific, well-documented rates, this diagram effectively works like a kind of galactic address, allowing anyone sufficiently advanced to calculate exactly where and roughly when this particular message originated. It is, in effect, a return address, etched carefully into gold, attached to a spacecraft that will likely drift through space for millions of years, after every trace of the civilization that built it has vanished entirely from Earth. Whoever eventually finds it, if anyone ever does, will be able to trace it back, not just to a general direction in the sky, but to a specific star, orbited once by a small blue and green planet that no longer exists in any form the finder would recognize. The scientists who chose pulsars for this purpose picked them specifically because their timing is so precise, so mathematically regular, that it should remain readable long after any human language has changed beyond recognition or vanished from use entirely. A pulsar does not care about empires or centuries or the rise and fall of civilizations. It simply keeps spinning, keeps flashing, on a schedule set by physics rather than by anything resembling memory or intention. That kind of steady, indifferent regularity was exactly what the record's designers needed. A language that would still make sense no matter how much time passed, no matter how completely everything else about Earth eventually changed. There is something profound and a little unsettling in leaving behind an address for a home that may not survive to receive any reply. And yet, the record was built anyway, address and all, because the people who assembled it believed the gesture itself mattered, regardless of whether anyone would ever actually respond to it. Let's think for a moment about the shape of the discovery itself, and why it took so long for NASA to say anything with confidence. Confirming a boundary this significant required more than a single interesting reading. It required ruling out every reasonable alternative explanation first, one at a time, carefully, before anyone was willing to attach the word confirmed to something this historic. Could the sudden jump in particle counts have been caused by a temporary solar event rather than a true permanent crossing? Could the change in magnetic field strength have come from some kind of instrument drift, slowly accumulating error rather than reflecting anything real happening outside the spacecraft? Each possibility had to be tested and tested again against every available scrap of data before scientists were willing to rule it out completely. This is not caution for its own sake. It reflects a deeper truth about how real discovery actually works, especially when the stakes involve rewriting textbooks that will be read by students for generations afterward. A claim this significant demanded a standard of evidence far higher than an interesting anomaly alone could satisfy. So the team waited. They waited for the plasma oscillation event to repeat months later, confirming the density measurement a second time, independently, before finally speaking with real confidence. They cross-checked the magnetic field data against every possible source of instrument error they could imagine, ruling each one out patiently, methodically, refusing to rush toward a headline before the evidence had genuinely earned it. Only once every reasonable alternative had been eliminated did NASA finally step forward and confirm, formally, that Voyager 1 had become the first human-made object in history to reach interstellar space. That patience is, in its own quiet way, part of the story too. Not the dramatic crossing itself, but the careful, unglamorous months of doubt and verification that came afterward. The part rarely mentioned in headlines, but the part that actually makes the discovery trustworthy. Real scientific certainty is built slowly, methodically, through exactly this kind of careful, patient doubt, applied again and again until only the truth remains standing. It is worth remembering that this entire process, the doubt, the rechecking, the waiting for a second confirming event, unfolded across a distance where every single question took nearly 2 full days simply to receive an answer. Most scientific debates on Earth can be settled within hours, sometimes minutes, by running a new experiment and reading the results almost immediately. This debate could not move that quickly, no matter how urgently anyone wanted an answer. Every stage of verification was stretched by the same unavoidable delay that governs everything about this mission. A reminder that even scientific certainty itself has to bend, patiently, around the basic physical limits of how fast information can travel across such an enormous, indifferent distance. Let's close this chapter of the story by returning, one final time, to the strange, uneven shape of the boundary itself. Because that unevenness may be the most quietly important discovery of this entire mission. For most of human history, the edge of our solar system existed only as an idea, drawn confidently in textbooks as a smooth, simple curve. Voyager proved that confidence was misplaced. The true boundary bulges in some directions, compresses in others, shaped by forces pressing unevenly against it from the wider galaxy beyond. It moves, subtly, breathing in and out across an 11-year rhythm tied to the sun's own natural cycle of activity. It may not even be a single, continuous surface at all, but something closer to a thick, blended, constantly shifting transition zone, especially where magnetic fields from 2 entirely different sources meet and struggle to separate cleanly. None of that complexity was visible from Earth. None of it could have been calculated with confidence, no matter how advanced the mathematics involved. It took an actual machine, physically present, patiently recording what it encountered, to reveal a truth no theoretical model alone could have discovered on its own. Every model built before Voyager reached that boundary was, in its own way, an honest best guess, built by careful people using the best mathematics available to them at the time. None of those models were foolish, and none of the scientists who built them were careless. They simply lacked the one thing no amount of careful reasoning could ever fully substitute for: direct experience of a place nobody had ever actually visited. That gap between careful theory and direct experience is one of the oldest tensions in the history of science. And Voyager's crossing is one of its clearest, most recent examples. A theory can be elegant, internally consistent, and still turn out to be incomplete the moment reality finally has a chance to speak for itself. That is not a weakness of science. It is closer to its quiet engine, the steady willingness to be corrected by something real, even after decades of confident, careful mathematics. Voyager did not humiliate the old models. It simply gave them something they had never had before, an actual answer, gathered patiently from the one place no equation alone could ever fully reach. That, in the end, may be the deepest lesson embedded inside this entire mission. Some knowledge cannot be reasoned into existence from a comfortable distance. Some knowledge can only be gathered by something willing to go there, wait there, and quietly report back exactly what it found, however strange, however inconvenient. however far it strays from what everyone confidently expected beforehand. Let's slow down and look closer at Jupiter, the first true test of everything this mission carried. Voyager 1 arrived in March of 1979, after nearly 2 years of silent, uneventful flight. Nobody expected fireworks from a planet made almost entirely of gas. Jupiter was assumed to be calm, layered, predictable, a giant ball of hydrogen and helium. The cameras began sending back images long before closest approach. At first, everything matched expectation almost exactly. Then, a navigation engineer noticed something strange near the edge of one image. A faint, curved shape hung above the limb of a small moon. At first, it looked like a processing error, a smudge, a flaw in the data. Someone suggested it might simply be another moon, caught by coincidence in the frame. Closer study ruled that out within hours. The shape was rising directly off the surface below it. It had the unmistakable form of a plume, arching outward against black space. That moon was Io, barely larger than Earth's own moon. Nobody had expected anything volcanic from a body so small and so cold. Small worlds were supposed to have gone quiet billions of years ago.
Io broke that assumption completely in a single photograph.
The plume rose nearly 200 miles above the surface. Material was being thrown out at speeds far beyond anything on Earth. This was the first active volcano ever confirmed outside our own planet. Scientists back on the ground could hardly believe what they were seeing. Within days, several more plumes were spotted across Io's surface. The moon was not simply active, it was extraordinarily active.
Later calculations suggested Io resurfaces itself faster than almost any body known. Lava flows there could bury an entire continent within a few centuries. The heat came from something unexpected, not from Io's own core alone. Jupiter's enormous gravity flexes the moon with every close orbit. That flexing generates friction deep inside Io's rocky interior. The friction produces heat, and the heat finds its way to the surface. It is called tidal heating, and Io remains its most dramatic example. Nothing in the mission's official goals had prepared anyone for this discovery. The 5-year plan had listed Io as a minor, uninteresting stop. Instead, it became one of the most important finds of the century. Jupiter itself offered its own surprises, quieter but just as important. The Great Red Spot, a storm larger than Earth itself, came into sharp focus. Its winds were measured directly for the first time in history. Bands of clouds churned and twisted in patterns nobody had modeled correctly. Lightning was detected flashing silently within Jupiter's turbulent upper atmosphere. A thin, faint ring was discovered circling the planet, invisible from Earth. No telescope on the ground had ever managed to detect it. Only a spacecraft passing close enough could finally reveal it existed. 2 more small moons were found, hiding in the planet's shadowed glow. Every new image seemed to overturn something scientists thought they already understood. The flyby lasted only a matter of days, yet reshaped decades of theory. Engineers on the ground barely had time to process each new image. Photographs arrived faster than anyone could fully analyze them in real time. Notebooks filled with hurried sketches, trying to keep pace with the data. Some scientists later admitted they barely slept during the closest approach. The spacecraft itself had no understanding of the excitement it was causing. It simply pointed its cameras where it was told and kept transmitting. Jupiter's gravity did more than provide images, it also bent Voyager's path. That bending was not an accident, it was carefully planned in advance. Engineers used Jupiter's mass to accelerate the spacecraft toward its next target. This technique is known as a gravity assist, or a slingshot maneuver. The idea is elegant, almost deceptively simple once explained clearly. A spacecraft approaches a massive planet along a carefully chosen path. The planet's gravity pulls the spacecraft in, curving its trajectory sharply. As the spacecraft swings past, it borrows a small amount of the planet's own momentum. The planet loses an immeasurably tiny fraction of its orbital speed. The spacecraft gains a substantial boost, far beyond what its engines could provide. No extra fuel is burned during this exchange, none at all. The energy comes entirely from careful geometry and nothing else. Without this technique, reaching the outer planets would have taken far longer. Some estimates suggest a direct flight to Saturn could have taken decades longer. Gravity assists turned an impossible mission into an achievable one. Voyager 1 used Jupiter's gravity to bend its path up and outward. That single choice would eventually launch it beyond the plane of the planets. It also meant giving up any future flyby of Uranus or Neptune. Every trajectory decision closed some doors while opening others permanently. Mission planners had to choose carefully, years before launch ever happened. There was no way to reverse a slingshot once it was completed. The math had to be correct on the very first attempt. A single miscalculation could have sent the spacecraft drifting uselessly into space. Engineers checked and rechecked every trajectory equation by hand and by computer. Confidence came slowly, built from months of careful, repeated verification. When the moment finally arrived, the maneuver worked exactly as calculated.
Voyager 1 left Jupiter faster and on a new course entirely.
9 months later, it approached its next great target, the planet Saturn. By November of 1980, anticipation on the ground had reached a new peak. Saturn's rings had fascinated astronomers since the earliest days of the telescope. From Earth, they appeared as a smooth, simple, almost painted band. Nobody expected the rings to reveal much more than that simple view. Voyager's cameras proved that assumption wrong almost immediately. The rings were not a single smooth structure at all. They were made of thousands of narrow, separate ringlets, tightly packed together. Some ringlets displayed strange, braided patterns, twisting around one another. Nothing in existing physics fully explained why braiding like that should occur. Small moons, later called shepherd moons, were found nearby the narrower rings. Their gravity appeared to be herding ring particles into narrow, stable paths. Even with that explanation, some ring behavior remained genuinely puzzling. Dark, spoke-like features appeared and disappeared across the rings in hours. These spokes seemed to defy simple orbital mechanics entirely. Scientists suspected electrically charged dust lifted briefly above the ring plane. A full explanation would take years of additional study to develop. Saturn's largest moon, Titan, drew intense interest from the mission team. Titan was known to have a thick, hazy atmosphere, unlike any other moon. Mission planners made a deliberate choice about how closely to approach it. Passing near Titan meant bending the spacecraft's path dramatically upward. That path would carry Voyager 1 out of the plane of the planets forever. There would be no way back down toward Uranus or Neptune afterward. The trade-off was accepted deliberately, planned years before the actual encounter. Titan's atmosphere turned out to be thicker than Earth's own atmosphere. Orange haze completely hid the moon's surface from every camera angle. Not a single detail of solid ground could be seen through that haze. Some engineers reportedly felt disappointed by the blank, orange images returned. Scientists were fascinated anyway by the chemistry the haze implied. Titan's atmosphere was rich in nitrogen, much like Earth's own air. Complex organic molecules were detected drifting within that thick orange atmosphere. For a moment, some researchers wondered about the chances of life there. Later missions would eventually confirm rivers and lakes of liquid methane on Titan. None of that detail was visible to Voyager 1's own instruments in 1980. Still, the encounter set the stage for decades of continued curiosity. A later mission would eventually carry a small lander directly to Titan's surface. That lander touched down more than 20 years after Voyager's brief flyby. None of it would have been planned quite the same without this first look. Saturn's own atmosphere revealed storms and banding patterns of its own. Winds were measured moving faster than anything ever recorded at Jupiter. Some equatorial winds approached 1,100 miles per hour in their peak bursts. The planet's pale golden color came from a thick blanket of ammonia clouds. Sunlight this far from the sun still lit Saturn with a soft, hazy glow. Every new image reminded the team how little had truly been known before. After Saturn, Voyager 1's planetary mission was effectively complete. No further planetary flybys were planned or possible along its new path. The spacecraft would now simply continue outward, watching and measuring as it went. Its twin, Voyager 2, chose an entirely different route through the solar system. That difference in trajectory would define two very different scientific stories. Voyager 2 stayed low, closer to the plane where the planets orbit. That choice preserved a rare opportunity, one that would not repeat for centuries. The outer planets had aligned in a way that allowed a single spacecraft to visit all four. Such an alignment last occurred more than a century before the mission launched. It would not occur again for roughly 175 years. Mission planners understood the rarity and built the trajectory around it deliberately. Voyager 2 flew past Jupiter, then Saturn, staying low and careful throughout. From Saturn, it continued onward toward a planet no spacecraft had ever visited. In January of 1986, Voyager 2 became the first spacecraft to reach Uranus. Uranus appeared almost featureless, a smooth, pale blue-green sphere in every image. Its extreme tilt meant the planet essentially rolled around the Sun on its side. Scientists still do not fully agree on what caused that unusual tilt. 11 new moons were discovered during that single, brief flyby. Faint rings, dark and difficult to detect, were confirmed circling the planet. 3 years later, Voyager 2 reached Neptune, its final planetary target. Neptune revealed deep blue clouds and winds faster than anywhere else measured. A massive, dark storm, later named the Great Dark Spot, was captured in detail. Neptune's moon Triton showed geysers of nitrogen erupting from its icy surface. To this day, Voyager 2 remains the only spacecraft to visit either planet. No other mission has been funded to return to Uranus or Neptune since. Voyager 1, meanwhile, had already left the plane of the planets behind. It carried no more flybys ahead, only the long, quiet road outward. Despite their different paths, both spacecraft carried nearly identical scientific instruments. Understanding those instruments helps explain how each discovery was actually made. The magnetometer was one of the most important instruments carried by either craft. It measured the strength and direction of magnetic fields along the flight path. Magnetic fields are invisible, yet they shape the behavior of charged particles everywhere. Near Jupiter, the magnetometer revealed a magnetic field far stronger than expected. Near the heliopause, decades later, that same instrument recorded something stranger still. The magnetic field's strength jumped sharply, but its direction barely changed at all. Existing models had predicted the field should tilt sharply at that boundary. Instead, it barely shifted, a small detail that puzzled scientists for years. That single measurement, from one modest instrument, rewrote assumptions about the boundary's shape. The cosmic ray detector served a very different purpose aboard the spacecraft. It counted high-energy particles arriving from deep within the galaxy. Inside the solar system, the Sun's own particles tend to dominate that count. Beyond the heliopause, interstellar particles should dominate instead, in theory. When Voyager 1 crossed that boundary, the detector's readings shifted dramatically. Galactic cosmic ray counts jumped sharply, almost overnight in the data stream. At the same time, particles associated with the Sun dropped just as sharply.
That combination gave scientists their clearest single signal of the actual crossing. Without this instrument, confirming the boundary crossing would have been far harder. The plasma wave instrument added another crucial piece of independent evidence. It could not measure the surrounding plasma directly, not by that point. An earlier failure had disabled the plasma instrument that once did that job. Engineers found a clever workaround, listening instead for plasma oscillations. Occasional solar eruptions would reach the spacecraft and disturb nearby plasma. Those disturbances caused faint oscillations the instrument could still detect and measure. From the frequency of those oscillations, scientists could calculate plasma density indirectly. It was an elegant repair for damage that could never be fixed directly. The instrument turned an old failure into an unexpected, workable solution. A spectrometer once studied the composition of light reflected off distant surfaces. It helped identify chemical elements present in the clouds of Jupiter and Saturn. It also studied faint ultraviolet light scattered across the outer solar system. Most optical instruments like this one have since been powered down completely. There was simply no longer enough electricity to keep every instrument running. Engineers had to choose carefully, instrument by instrument, year after year. Priority went to whichever instruments still returned genuinely useful, irreplaceable data. Cameras were among the very first instruments switched off permanently. There was nothing left worth photographing in the empty dark beyond the planets. Fields, particles, and plasma mattered far more than any remaining image could. Each shutdown decision was made carefully, and never without real reluctance. Every instrument still running today represents a deliberate, hard-won survival.
Now consider a single photograph, taken not for scientific need, but for meaning. In 1990, Voyager 1 had already completed every planned scientific objective. Someone suggested turning the cameras around, one final time, toward home. The scientist who championed this idea was Carl Sagan, a well-known astronomer. He argued that a single photograph could carry weight beyond pure data. Not everyone agreed at first. Some worried about risk to the cameras. Pointing directly near the sun risked damaging delicate camera components permanently. After careful study, engineers confirmed the maneuver could be performed safely. On Valentine's Day in February of 1990, the command was finally sent. Voyager 1 turned its cameras back toward the solar system one last time. It captured a series of images, 60 in total, of the planets. Earth appeared in only one of those frames, a single, pale pixel. Less than a single pixel wide, caught in a stray beam of sunlight. Sagan later described that pixel in words many people still remember. He called it a pale blue dot, suspended in a sunbeam. He wrote that everyone who ever lived did so on that dot. Every war, every celebration, every ordinary morning happened on that single pixel. The photograph carried no new scientific data of measurable importance. Its value was entirely different, entirely human, entirely about perspective. After this final photograph, the cameras were powered down for good. They have never been turned back on again, not even once. There was no longer any scientific justification for the power they required. That single frame remains the last photograph Voyager 1 will ever take. Now consider the people who have kept this mission running for decades. The original engineers who built Voyager 1 have mostly retired by now. Several have passed away in the years since the spacecraft launched. Their detailed knowledge lived largely in memory, not always in written form. Younger engineers had to learn systems built before most of them were born. Some documentation existed only on paper, stored away in old physical archives. Certain programming languages used aboard the spacecraft are no longer commonly taught. A handful of engineers deliberately studied those languages just to keep pace. Understanding decades-old code became almost a specialized historical skill. Every command sent still has to account for outdated, limited onboard memory. The spacecraft's entire computer holds less processing power than a modern watch. Engineers must think in a language of extreme scarcity and careful precision. Nothing about sending a command today can be rushed or careless. A single mistake could permanently silence an instrument that took decades to understand. The team meets regularly, checking signal strength, power levels, and instrument health. Every year, the available power continues to shrink, slowly and predictably. Every year, another difficult decision arrives about which system to disable next. Engineers describe the process less like flying a spacecraft, more like triage. They choose, carefully, what stays alive and what must finally go quiet. There is no dramatic ceremony attached to shutting an instrument down. There is only a command, sent carefully, and a quiet loss of data. Some engineers have worked on this mission for their entire careers. A few began as students and are now nearing retirement themselves. They speak about the spacecraft with a tone usually reserved for old friends. It has outlived colleagues, outlived careers, outlived entire technological generations already. The question everyone eventually asks is simple. How much longer can this last? The plutonium aboard Voyager 1 decays at a slow, fixed, predictable rate. Power output drops by roughly 4 watts with every passing year. At some point, there will not be enough electricity to power any instrument. Engineers currently estimate that moment will likely arrive sometime in the 2030s. The exact year remains uncertain, dependent on which instruments still run by then. Some instruments will likely be shut down years before the spacecraft goes fully silent. Even after every scientific instrument is powered down, the transmitter may continue briefly. Eventually, even that faint signal will fade below what can be detected. At that point, Voyager 1 will still exist, drifting silently through space.
It simply will no longer be able to tell anyone that it does.
No dramatic failure will mark that moment, only a quiet fading of signal. The spacecraft itself will remain intact, coasting onward for billions of years. Its instruments will fall silent long before its physical journey ever ends. It will pass no more stars closely for tens of thousands of years. It will carry its golden record onward regardless, whether anyone is listening or not.
The mission was never truly measured in years. Not really. Not at its heart.
It was measured in careful choices, made one at a time for decades. Every flyby, every repaired instrument, every rewritten line of code added to that total. Jupiter's volcano, Saturn's braided rings, a pale blue dot, an aging team of engineers. Each one is a small chapter within one much larger, quieter story. That story is still being written, quietly, 4 watts at a time. Let's return briefly to the instruments because each one still matters individually. The plasma science instrument once measured the speed of the solar wind directly. It worked flawlessly for years, tracking particles streaming outward from the sun. Then, in the cold beyond Saturn, a critical component quietly failed. Engineers never fully agreed on the exact cause of that failure. Cold, radiation, or simple age were all considered possible explanations. Whatever the cause, the instrument stopped returning reliable readings permanently. For years afterward, that gap in data seemed like a permanent loss. Later, other instruments were cleverly repurposed to estimate similar information indirectly. The plasma wave instrument, listening for oscillations, filled part of that gap. Necessity, decades into the mission, forced a kind of quiet, careful improvisation. The low-energy charged particle instrument tracked slower-moving particles nearby. It helped distinguish particles native to the solar system from outside arrivals. Together with the cosmic ray detector, it painted a fuller picture of the boundary. Neither instrument alone would have been fully convincing on its own. Combined, they offered a picture strong enough to convince skeptical scientists. That is often how spacecraft science actually works, quietly, through overlapping evidence. No single dramatic reading usually settles a major scientific question by itself. Instead, multiple instruments slowly build agreement, piece by careful piece. The ultraviolet spectrometer, before it was retired, studied faint light from distant gas. It helped map hydrogens scattered thinly throughout the outer solar system. That mapping helped scientists understand the size and shape of the heliosphere itself. Even instruments not designed for the boundary ended up helping describe it. Nothing aboard Voyager 1 was built with total certainty about its future use. Engineers designed for flexibility, knowing some original goals might shift over time. That flexibility proved essential decades later, far beyond anyone's original expectation. Now consider more closely how Voyager 1 and Voyager 2 finally compare. Both launched in the summer of 1977, only 16 days apart. Voyager 2 actually left Earth first, despite carrying the higher mission number. Voyager 1 traveled a faster, more direct route, catching up along the way. That faster route let it reach both Jupiter and Saturn first. Its higher number came from the order scientists expected encounters to occur. Voyager 1's path ultimately carried it up and out of the plane of the planets. Voyager 2 remained low, preserving its shot at Uranus and Neptune. Their instruments were nearly identical, built from the same original blueprints. Their outcomes, however, diverged enormously, shaped entirely by trajectory choices. Voyager 1 crossed the heliopause first, in August of 2012. Voyager 2 followed 6 years later, crossing in November of 2018. That gap allowed scientists a rare chance for direct comparison. If both crossings matched closely, the boundary might be simple and uniform. If they differed, the boundary might be far stranger than anyone assumed. The two crossings did not match as closely as many had hoped. The distances differed, and so did several other measured details. Voyager 2 still had a working plasma instrument, unlike its older sibling. That instrument allowed direct measurement of the interstellar plasma's temperature. The temperature measured was unexpectedly high, hotter than most models predicted. Voyager 1 could only estimate similar information indirectly through other instruments. Having both spacecraft in different regions made the picture far richer. A single spacecraft crossing once might have looked like a simple, tidy boundary. Two spacecraft, crossing years apart, revealed a boundary that breathes and shifts. That difference alone justified building two spacecraft instead of only one. Redundancy was never just about backup. It was about genuine comparison. Mission planners in the 1970s could not have predicted this scientific payoff. They built two spacecraft, mainly to guard against losing one along the way. Decades later, that redundancy became one of the mission's greatest scientific assets. Sometimes the most valuable outcomes arrive from decisions made for entirely different reasons. Consider, too, how fragile the entire gravity assist plan truly was. Every trajectory depended on a precise, narrow launch window in 1977. Missing that window by even a few weeks would have changed everything. The rare alignment of the outer planets would not have waited. Engineers had exactly one practical opportunity to attempt this ambitious route. There was no simple way to reschedule an alignment spanning decades. That pressure shaped nearly every early decision made about the mission. Backup systems, redundant instruments, careful testing, all stemmed from that narrow window. Nothing about launching in 1977 could be treated as routine or safe. Every gravity assist afterward depended on the accuracy of the one before it. A small error at Jupiter would have compounded by the time of Saturn. Engineers rechecked trajectory calculations obsessively, long before any modern computing power existed. Slide rules, early computers, and careful human review all played a role. Confidence was earned slowly, through repetition, not assumed from the start. When each maneuver succeeded, it validated years of painstaking preparatory work. Looking back, the entire outer solar system tour reads like a single continuous gamble. At every stage,
A single error could have ended the story early. Instead, one careful success led naturally into the next opportunity. Jupiter's slingshot enabled Saturn's approach, and Saturn shaped everything that followed. Titan's flyby closed off future planets, but opened a new kind of mission. Voyager 1 stopped exploring worlds and started exploring nothing but empty space. That transition, from planetary tourist to interstellar wanderer, was not glamorous. For years, it produced far less dramatic imagery than the earlier flybys. Yet the empty space it studied held some of the mission's strangest discoveries. A wall no one could see, a field that would not turn. None of that would have been reachable without the earlier gravity assists. Every discovery in the years since traces back to those precise early maneuvers. The volcano on Io, the rings at Saturn, the pale dot near the Sun. All of it depended on physics understood well enough to bend a trajectory. All of it depended on a team willing to trust that math completely. Decades later, the same spirit of careful trust keeps the mission alive. Engineers still trust old code, old memory, and old careful documentation. They still trust that 4 watts a year is a number worth respecting. They still trust that somewhere, a faint signal is worth listening for. That trust, built in 1977, still guides every decision made today. Let's take one more quiet pass through the numbers, slowly, because numbers this large deserve to be repeated more than once before they can truly settle into the mind. 14 billion miles. A distance that light, moving faster than anything else in the universe, still needs over 22 hours to cross. 47 years of continuous flight, powered by a slowly fading chunk of decaying plutonium, no larger than a small household object. 4 watts lost every single year. A quiet, steady tax paid without exception, without pause, without any possibility of appeal. 2 spacecraft, launched 16 days apart, in a single distant summer, both still sending faint signals home. Both still teaching us things nobody predicted when they first left the ground. 1 golden record, carrying 90 minutes of music, greetings in 55 languages, and a return address written in the steady, patient language of pulsars. 40,000 years before it passes anywhere near another star. 175 years before the rare planetary alignment that made this entire mission possible will ever occur again. Numbers this large are not really meant to be understood all at once. They are meant to be sat with, slowly, the way you might sit with the sound of the ocean, letting the scale of it wash over you gradually, without needing to fully grasp its edges. Voyager 1 does not know any of these numbers describe it. It does not know it carries the record, the mystery, the message, the quiet weight of an entire species reaching outward. It simply continues, faithfully, exactly as it was told to, drifting through a darkness that has no morning waiting on the other side of it. And somewhere back on a small blue and green world, a species that built it continues to watch, and wait, and wonder, patiently listening for whatever faint signal arrives next, for as long as one still comes. 2 spacecraft, launched 16 days apart, in the summer of a single distant year. Built to last 5 years. Still flying after nearly 50. Still sending faint signals across a gulf of distance that swallows the meaning of ordinary numbers. Still carrying a golden record meant for no one in particular. And everyone who might ever wonder if they are alone. 47 years of continuous flight. And still counting. 1 spacecraft, built from technology older than most of the people reading about it now. Still teaching us things nobody predicted. Still raising questions nobody has fully answered. A message aimed at no one in particular, and everyone at once. A machine built by human hands, carrying human curiosity, farther than any human will likely travel for generations to come. Let's pause once more, before the very end, and think about what it means that this entire story rests on something as fragile as electricity slowly running out. Every discovery described tonight, the magnetic field that would not turn, the wall that sat billions of miles from where it should have, the density that jumped by a factor of 40, the record etched in gold and aimed at no one in particular. All of it exists only because a small, warm chunk of decaying plutonium has kept producing just enough electricity to keep listening a little longer. There was no guarantee any of this would happen. There was no promise in 1977 that a 5-year mission would still be speaking to us in 2026. There was only careful engineering, conservative choices, and a strange kind of quiet faith that building something well enough might let it matter far longer than anyone officially expected. That faith paid off, decade after decade, further than anyone reasonably had the right to hope for. And somewhere in the 2030s, it will finally run out. Not because anything failed, but simply because the plutonium will have decayed as far as it ever could, exactly as physics always said it would. When that happens, there will be no more anomalies reported, no more mysteries raised, no more faint signals arriving after a patient, 2-day wait. Only silence and a small, cold machine drifting onward regardless, carrying everything it was ever given into a darkness that has no need of electricity to continue existing. Somewhere in that eventual silence is the quietest kind of ending imaginable. Not a failure, not a tragedy, simply a long, slow completion of something that was never meant to last this long in the first place, and somehow did anyway. No new commands scheduled, only the quiet continuation of a journey that began with a countdown and will end, eventually, without one. Somewhere out past the edge of everything familiar, past the last line any diagram has ever drawn with real confidence, 2 small machines drift onward through the dark, not searching, not signaling for help, only witnessing, quietly on our behalf, a frontier we ourselves may never personally cross. Consider, one last time, how strange it is that a project born from a 5-year plan became a lesson in patience stretched across half a century. Consider how a single failed instrument in 1980 forced an entire team to become creative decades later, improvising a solution nobody had ever needed before. Consider how a moon wrapped in orange haze quietly redirected an entire spacecraft's destiny, trading 4 distant planets for one close, uncertain answer. Consider how a magnetic field, aligned in a way nobody predicted, still sits unexplained in scientific papers written this very year. Consider how a temperature hotter than the surface of a star can surround a machine without ever once warming it. Consider how a boundary once drawn as a smooth, confident curve turned out to be lopsided, breathing, and still not fully mapped. Consider how a handful of engineers, decades apart in age, learned to think like one another simply to keep an old machine speaking a little longer. Consider how a record made of gold, carrying laughter and heartbeats and music from 100 different cultures, drifts now through a silence that may never answer it. Each of these threads began as a small, practical decision, made by ordinary people doing careful work, decades before any of them could know how far their choices would eventually travel. None of them set out to build a message meant to outlast civilizations. They only set out to build something reliable enough to survive 5 years among the outer planets. Everything after that has been an unplanned inheritance, handed forward quietly. One careful generation of engineers at a time. None of it required a grand, sweeping vision announced at the very beginning. It required only a long chain of small, faithful decisions, each one made by someone who understood their part clearly, without needing to see the entire, unfinished picture stretching out decades ahead of them. That may be the quietest, truest kind of legacy a project like this can leave behind. Not a single dramatic achievement, but an unbroken thread of careful attention, passed patiently from hand to hand, for far longer than anyone at the very start had any real right to expect. Think, too, about everyone who has quietly worked to keep this signal alive, most of them unknown outside a small community of specialists. Engineers who learned an obsolete programming language specifically to understand instructions written before they were born. Technicians who tracked down decades-old paper manuals in storage, because no digital record ever fully replaced them. Scientists who waited months for a single solar eruption to arrive, just to confirm one number everyone was already fairly confident about. None of these people will have their names remembered the way the mission itself will be remembered. Most of their work will simply blend into the long, quiet history of a machine that refused, again and again, to stop functioning on schedule. And yet, without every one of those small, careful, mostly invisible efforts, the story tonight would have ended decades ago, quietly, without fanfare. Long before any of these anomalies were ever found. Discovery, it turns out, rarely belongs to a single dramatic moment. It belongs to thousands of small, patient choices, made faithfully, across years nobody was watching closely, by people who understood that some kinds of understanding simply take longer to arrive than a single career allows. We built something that outlived our own certainty about what it would ever find. We are the species that sent a golden record into a silence it may never break. We are the species that kept listening anyway, year after year, long after the original mission had already succeeded by every reasonable measure. We are the species that rewrote decades-old code across 14 billion miles, simply because giving up felt worse than trying. We are the species that measured a wall we could not see, using a borrowed instrument never designed for the job, and trusted the answer only after checking it twice. We are the species that built a message with almost no chance of ever being received, and sent it anyway, because the sending itself seemed to matter. 2 machines, 1 golden record each, 47 years, and still counting, drifting outward, quietly, into a darkness that has no need of an audience at all. Brief sparks of curiosity, thrown outward into an ocean of dark, patient enough to wait 40,000 years for an answer that may never come.